Okay, let's tackle the next question. Mary asks, can the same pathogen cause different disease excuse me, in different hosts? So Mary asked, why doesn't Mary start with the discussion?
The short answer is yes. And it's really I think one of the most fascinating aspects of infectious disease. It also confounds a lot of the research that we do, because it means we can have a virus or any pathogen in hand, but if we're not working with its natural host, we may not be able to understand the disease. So what are some examples? The typical examples are where the organism in one animal causes no disease, and then in another animal causes sometimes fatal disease. And there's a good example of this with herpes virus in elephants. So in the zoos, African and Asian elephants often were co-housed. One of those species is highly susceptible to this virus. The other one is infected, and there's no problem. That ripples through many infections. The HIV infection, that virus was initially a primate virus where there's very little disease, and we see very similar patterns in the feline viruses, the cousin of HIV, where wild cats in the United States, like cougars, carry this virus, no disease, but domestic cats develop an immunodeficiency syndrome as well. But we also have examples here where we get different types of disease. And again, that's interesting because it allows us to look at some of the host genetic and immunological features that may lead to a disease, say, of the respiratory tract versus the GI tract. And again, there's quite a few examples of that. So again, short answer, yes, but longer answer.
Right, and the most classic example of that would be influenza, right, which is a GI pathogen in waterfowl and is a respiratory pathogen.
Well, it's hardly even a pathogen. It's
well, it's
just
true,
shed.
Sure, right. It lives in the GI tract of waterfowl, right, but it causes disease in the respiratory tract of humans.
It can be shed. Actually, it's likely shed from the GI tract in some humans, and that.
Okay.
And part of that is that our respiratory tract and our GI tract are not independent. When you have a respiratory tract infection, you're coughing things up,
right.
Swallow them, and they get passed. So, but it's a point well taken that the same virus, may have the ability to replicate in different sets of cells and different animals. All really cool questions.
If I could bring up a different version of this, there's been quite a discussion on the boards about polio, and that's
a good one.
Multiple older members of my family experienced, and hearing them talk about it, having polio in a leg, or polio in the back, or polio, I always felt odd to me to locate it in a place, right? But can it actually locate in different parts of the body? And it must be very difficult then to figure out when someone might have something if it looks like things are locating or expressing themselves very differently. That must make this all very challenging.
So the polio is probably not the best example of that, but to stay with your example, it actually is very cool. It's a GI tract infection. Okay, a subset of those viruses actually can gain entry to the central nervous system, and then depending on where they end up in the central nervous system will depend on the type of lesion that you see. So that's where the diversity comes. But the more interesting aspect is that for most people, this is a virus that replicates in the GI tract. And there's some real cool work that's being done here that suggests that the virus that you're infected with replicates in the GI tract. But we've talked about RNA viruses having, they are able to generate a lot of diversity because the enzyme that they use to replicate themselves doesn't have a proofreading infection. So you get these clouds of viral variants. And in some cases, by chance, you may get a virus that then has the ability to enter the central nervous system. So if you make a virus that has a very high fidelity, low error prone polymerase, you tend to not get viruses that enter the central nervous system. And they're considering using that as a vaccine strategy. So, and there's been some questions on the boards too. Why can't we do these manipulations of viruses, for good? Well, we are.
Can you maybe talk a little bit about how this huge sort of variance in expression of an infection from completely asymptomatic to totally devastating, how that affects disease dynamics?
Yeah.
Because there's a lot of there's a lot of discussion about that. Sorry to put you on the spot.
Okay, 2 minutes or less.
Yeah, right. 2 minutes or less.
And then make like world peace.
Yeah,
I know.
right.
There was famous
And if you
cholera
answer
and
this right,
dengue
it's a Nobel
papers.
Prize.
Right. Well, there's two sides to that. There's the impact that it has on the dynamics of the disease, and there's also the impact that it has on our ability to observe those dynamics, to detect what's going on, right? So in particular, to some extent, unless that expression of symptomology is tied to transmission itself, which it isn't always necessarily the case, then actually it really shouldn't implicitly have any effect on the dynamics of the disease. Dynamics are just going to go as they go. We're only going to see what we can see, and so we might then misinterpret flare-ups of disease of clinical disease as being an increase in cases or a change in the transmission dynamic, when in fact it's really just the natural progression is going on. So I think the real challenge is the interplay between our ability to observe this thing or not. There are cases where it's where these issues are uncertain. Meningococcal meningitis in sub-Saharan Africa is a classic example of this, where the jury is really very much still out. There's an environmental component. So this is a commensal bacteria that's around all the time. It's a suite of several different bacteria that are around in our lungs all the time, and certain environmental conditions, either particulate matter from being in poorly ventilated areas, or the very dry winds and dust that blow in off the Sahara on a yearly, seasonal basis, can cause a lot of lesions in the respiratory tract and allow for the invasion of this bacterium into the bloodstream. And so what we tend to see are these massive flare-ups of people with disease, which is expressed when this bacterium gets into the bloodstream and then causes disease within the central nervous system. That isn't necessarily that doesn't necessarily mean that transmission is picking up at the same time, just because you're seeing more people as sick. However, when we look closely at the patterns, there is some indication that in fact, when the numbers of people that are sick with meningitis disease, that we actually do also see greater spatial patterning, right? As we see flare-ups that all tend to be highly localized, which might be consistent with the idea that in fact, as we see more disease ramping up, we are seeing an increase in transmission. So it raises more questions than it does answers, right? But the inherent problem really is our ability to see who out there is sick and who out there isn't.
I think it's really an important point, and I think we may be at sort of a pivot point. Prior to maybe a few years ago, symptomology, the clinical disease, was critical for us to identify that an infectious process was going on. We're getting to a point now with these new sequencing technologies and probably other technologies that have diagnostics on a handheld device, okay, that will be able to identify these organisms, whether or not you have the clinical disease. So right now, the disease outbreaks is just that. You have to have disease. We come up with a clinical case history that's distributed, so other individuals will say, if you have these 10 syndromes, then you're likely to have this infection, okay? And then we use that to count infections, and the epidemiologists use those data. At some point, we may just be able to just take our phone, touch it, and say, oh, you have virus 1, 2, 3, 4.
One day.
One day.
That's next year, right?